Welcome to this lesson video on asphalt placement, operation, and equipment. We have four learning objectives to cover in this lesson, where we will learn about the different asphalt placement equipment and calculate their different production rates and speeds. If you have not done so already, please check the other lesson on asphalt production, where we learned about the asphalt placement, asphalt material properties in production plants. Asphalt production and placement happen at different locations, but they are really tied and synchronized together. Here we will assume that the asphalt plant production is set as the target pace, and the placement operation will follow the plant production rate. The production of an asphalt batch plant is calculated using the shown simple formula as the rate of dividing the weight of each produced batch on the batch production time. The formula also accounts for the plant efficiency factor. This is an example of a batch plant that produces 8-ton batch every 1 minute with a plant efficiency of 90%. When applying the formula, the batch production rate is 432 tons per hour. Once the asphalt production is determined, we need to match with it the rates and speeds of the placement equipment. Placing the asphalt requires preparing the soil base or binder or the binder course, hauling the asphalt from the batch plant, paving the asphalt using the paver, and compacting the mat laid behind the paver. Let's learn about each of these placement processes and equipment. The surface that will receive the asphalt needs to be prepared by removing any old pavement mat, sweeping any dirt or unwanted objects, and spraying the liquid asphalt. Over its life cycle, asphalt pavements get minor treatments for potholes and cracks. Over the years, these minor treatments lose effectiveness, and more extensive rehabilitation work need to be done by removing the top wearing course of the asphalt and placing a new one. However, the good thing about asphalt is that it is recyclable to some extent. Asphalt milling machines are used to provide and retrieve old asphalt, which can be recycled by hauling it to the asphalt production plant or recycling it right away on site. The retrieved asphalt from the milling machine becomes the possible recycled material for what's called the reclaimed asphalt pavement RAP. The pavement design standards allows for using RAP materials to construct new pavements. But RAP material is limited to be around 25 to 30% of the hot mixed asphalt, as the asphalt content in the RAP material has been oxidized over its previous life years. This photo here shows the conveyor in the batch plant carrying the aggregates and the RAP material to the drum dryer. Another recycling approach is to use the RAP material right away on site to produce a new pavement. This operation is called crush heat relay, and also known as pulverize and relay. This is done by first spreading the retrieved asphalt windrow using a grader. Then a train of crushing, conveying, and paving equipment take on the RAP material and produce a new pavement. This approach saves a lot of money by skipping the whole back and forth from the batch plant, but there is less ability to refine or modify the RAP before recycling it. The retrieved asphalt milling can be recycled on-site by placing it on the shoulder strip along the road. This milling windrow is spread and compacted afterwards to provide a leveled shoulder surface. Sweeping trucks are used after milling machines to clear the surface from dust and foreign material that can reduce the cohesion of the surface with the new pavement. After sweeping, the liquid asphalt is sprayed using the distributor trucks. The distributor trucks spray liquid asphalt on top of the aggregate base to create a prime coat, or on top of an existing asphalt binder course to create a tack coat. The asphalt is kept in its liquid state by heating it with burners inside the tank and adding emulsions to it. The asphalt is sprayed from the back of the truck using a spray bar that's typically the width of a standard traffic lane. The specifications or material manufacturer will call for a specific asphalt temperature and application rate as how many gallons sprayed on a unit area. For liquid asphalt distributor, it is important to decide on the truck driving speed and the total liquid asphalt volume to satisfy the required application rate. This formula relates the required application rate to its three main operational variables: the spray rate, the truck speed, and the spray bar width. This means that by fixing two variables, we can get the value of the third variable to satisfy a required application rate. We can also see higher application rates require faster spray rate and slower truck driving speed. For the same speed and spray rate, we need smaller spray bar to have a greater application rate to concentrate the sprayed liquid on a smaller segment of the road. The second formula here can be used to calculate the total volume of liquid asphalt that is needed for the required application rate on the whole road area of length LT and width WT. Back to the big picture, we are done with the base and mat preparation. Next, let's see how the asphalt is hauled from the batch plant to the paver. Asphalt concrete is delivered to the site using dump trucks, similar to those used in soil hauling. But these trucks are equipped with special boxes and have some tougher delivery requirements. The warm temperature of the hauled asphalt should be protected by having insulated truck box walls and cover sheets. The goal is to have the required warm temperature uniformly over the mix volume, otherwise the outer part of the asphalt will cool and segregate from the rest of the mix. The trucks can have two dump designs depending on how the asphalt dumped, depending on how the dumped asphalt will be handled. The rear dump trucks are used when the load is dumped directly to the paver. During dumping, the truck attached to the paver and follows the paver's speed in moving and paving the asphalt. The bottom dump trucks leave behind them a windrow of asphalt that can be handled with a material transfer vehicle or spread with a spreader. Asphalt pavers are expensive and sophisticated equipment that are a form of a factory on wheels. The paver receives the asphalt concrete mix in its front hopper and delivers it to the rear screed through a conveyor truck tunnel. Just before the screed, the auger receives the asphalt concrete from the conveyor and works on distributing it evenly over the screed. The screed produces the initial cross-section shape of the produced asphalt mat. It can control the width, the depth, and the slope of the new pavement. The screed may look simple, but its success in creating the correct depth of the pavement depends on multiple factors like its angle of attack, its toe point height, the paver speed, and the flow of the asphalt feeding to the screed. Material Transfer Vehicle, MTV, is another equipment that can be used in asphalt paving operation, as it can help overcome some operational challenges. The MTV is a middle equipment between the trucks and the paver, as it receives the truckload, keeps remixing it and heating it, and delivers the load to the paver. In this way, the MTV helps to improve the operation efficiency in multiple ways. First, the MTV helps to reduce the negative impact of truck hauling bunching phenomena when haul time variability results in truck unavailability even if the crew is well balanced. Second, it relieves the paver from the need to connect to the truck and push it during the paving process. This simplifies the whole operation and reduces the mechanical loads on the paver. Third, the MTV improves the asphalt concrete quality by remixing it until it is delivered to the paver. However, the MTV is not cheap, and it is a question of paying extra money to smoother paving operation and better pavement quality. As the asphalt plant is a significant capital asset, the placement, production, and equipment follow the rate of producing the asphalt from the plant. Also, it is critical to maintain a constant travel speed of the paver to produce a quality pavement. So we need to plan well for the two main links in this production process: the number of asphalt hauling trucks and the paver speed. We will use this simple formula to calculate the number of trucks needed to deliver the asphalt at the same rate it is produced. The truck production is here assumed to depend largely on its transit time, not much on the time of dumping the load in the paver. The paver speed is calculated in two steps. First, we calculate the weight of 1 feet of the full width pavement by multiplying the volume of this 1 feet segment and the design density of the pavement. You can notice the interesting way of representing the volume and density using square yard inch instead of cubic yards or feet. This is because the pavement design manuals use pound per square yard inch units for the required density. The second step is to calculate the paver speed in feet per minute to match the plant production, considering the pavement weight needed for every 1 foot of the road. We are almost done here. The last step in placing the asphalt is compaction. Asphalt compaction can be done by 3 compactor types: vibratory drum roller, static steel wheel, or pneumatic tire. We covered these compactors in the soil compaction lesson. The rollers compact the pavement by covering the full width of the pavement in laps. The rollers drive on each lap back and forth for a specific number of passes with a maximum roller speed, which both parameters are outlined in the specifications. Also, the laps are required to overlap to a minimum distance to account for the reduced compaction at the ends of the roller width. Also, the roller will extend over the end of the pavement with some distance to make sure the edge is well compacted. Planning the asphalt compaction operation requires determining the roller types and speeds to match the rate of asphalt production and placement. The productivity of the roller compaction is dependent on the following parameters, which we already covered in the previous slide. The last parameter is to account for the non-productive roller times that require increasing a little the ideal roller speed to compensate for maneuvering. We start the calculation process by calculating the required compaction width, RCW, which equals the pavement total width plus the roller extension over the edge. Also, we calculate the effective rolling width, ERW, of the compactor by deducting the overlap from the roller width. We then calculate the number of laps, NLP, by dividing RCW over ERW. We calculate the total number of passes for the whole pavement width by multiplying the number of laps and the number of passes per lap. Then we calculate the required speed of the roller, RSR, by multiplying the paver speed, the number of pavement passes, one or more adjustment factors, and dividing by an efficiency factor. You can see that always the roller speed is much faster than the paver speed, as the roller go many passes behind the paver, and they are required to be closely following the paver to compact the fresh pavement. The last step is to check if the required paver speed is achievable and not limited by the maximum roller speed that's imposed by the specifications. If this condition is satisfied, then a single roller is sufficient. Otherwise, the number of rollers required will be increased by rounding up the division of the required and maximum number of rollers. That's it for this very interesting stuff on asphalt placement. Please check the other exercise videos to apply what we learned here on the production calculations for liquid asphalt distributors, pavers, and rollers. Thank you.